Yeah, good afternoon. Thank you for the introduction. And thanks to the OpenSFS committee for having me here. So today's topic is high-performance cloud-native Lustre and object storage with active-active. It's unusual deployment, so that's what I'm going to talk about. So before I talk about object storage, let's go back to the history of object storage, just for there's the irony out there. So OST, it's an object storage target, but during the .com time, so there was a SCSI standard, the ambitious standard to develop this object storage, but that never materializes. And now, at the same time, the Amazon, right, they started S3, and that became the object storage now. And they built the FSX Lustre on local SSD, but not S3 until now. That was mentioned 1 hour ago. So what's happening here? So with the ZFS VDEV, so we are able to bridge that gap. So a little bit intro to what is this object storage and native ZFS VDEV. So that's a tiny storage abstraction layer. That's a kernel module that sits right next to ZFS VDEV module. And it's a translation layer. It takes a ZIO directly from ZFS, and then it passes on to a user level Go program called object backer. So this object backer makes use of all these barrel proven Go SDKs from the vendor supplied. For example, for S3, we use the AWS SDK and Azure Blobs, etc. As you see on the other side, the ZFS IO are being translated to REST APIs one-on-one. So it naturally fits in there. The ZFS write goes in as the put operation and read as a get. And interestingly, ZFS provides a trim. And you could recover your, reclaim and free up the blocks or immediately released so that you don't have to pay for the storage API cost. And then Zinc, the F-Sync is translated to, we take care of that. So compared to a fuse layer, this is a kernel module. So there's a lot of advantages in using a kernel module compared to fuse, and because of that, we are able to achieve extreme throughput. Like for example, we could do like 13 gigabytes per second on a 150 gigabits per second Ethernet. So here is the architecture that's getting deployed. So how we simplified it is, it's just 2 nodes. And with just 2 nodes, we try to combine all the services of Lustre. On one node, so you could run the MGS, MDS, and one of the OSTs. And in the other node, you could have the second OST. So, and you see all the components right there on the top. So the MGS and one LNet, everything is in there. And each node can run any role. So the roles can be moved easily across the node because they use a floating VIPs. And so even though the system has 2 VIPs, you just need only 1 VIP for the MGS. So the differentiation here is at the bottom. So those bucket icons are really ZFS VDEVs. And you could consider one bucket as one OST. So that powerful it is. That much parallelism is packed right inside that one node. So easily you can compare this architecture. If you compare it to a traditional architecture, this could be like a 12-node OST right there, and a 4-node comprised of MGS, MDT, and yet another OST. So things like that. So everything is packed right into a 2-node active-active HA. Everything is simplified, and they get deployed by Terraform. Everything happens in 2 minutes. Because we talked about for bringing up a petabyte of file system with the ext4, it's going to take a while, but zpool creates a OST just like that. So the time-consuming aspect over there is the MDT again, and so ext4. But again, luckily it is using that only for metadata, and so you tend to provision a smaller size. And the object storage could be arbitrarily any size. So no more full OST or none of those issues. It's just like a bottomless object storage, and the capacity is unlimited, and you only pay for what you actually use. Even though you could have created a zpool of exabyte of zpool, you don't really pay anything until you start writing into the pool. So that's the advantage of using object storage directly with Lustre. So here, the cover two more components in there. The MDT sits on the NVMe, it's a smaller size. Similarly, for the OST, you need a couple of smaller SSD. So they are called the special VDEVs. If folks familiar with the ZFS architecture, it's a hybrid architecture wherein you could have, just like the Lustre also has something similar to that now with your DOM and things like that. So what this special VDEV does is, it's not about intelligent tiering, it's different. It just, everything goes direct, everything's hot. Smaller IOs, depending on the sizes, it goes direct to the NVMe. Based on the workload, and if it's a larger size, like 1 MB, or you could configure it with your parameter special VDEV block. So that gets shipped to the object, the high latency object storage. And these days, ZFS provides an option wherein you can use the special as ZIL for consistency. So yeah, this is much cleaner for you folks because it's a live shot of what's happening in all the software components. So whatever shown in the block diagram, this is how it appears. So you could pretty much compose it in 2 minutes with Terraform, and so no more, it solves a lot of problems. Object storage can be any size, and you don't have not too much to worry about multi-tenancy here, no QoS challenges, because if somebody wants one more namespace, just compose yet another cluster for them. So again, for zooming into the buckets, they actually form the 12 OSTs inside. So you don't have to do any migration, no copy in, copy out, because everything, the data is always on the object storage and accessed by ZFS. So with the zpool VDEV, it is doing the striping, and the NVMe special VDEV does the allocation for small IOs. So if you want to add capacity, just add a bucket. So and the zpool capacity increases. So this slide gives what you could, the performance you could get out of this particular node. So on a GCP C4 with 144 cores with 150 gigabyte bits per second tier 1, so you could achieve, the local ZFS can do about 13 gigabytes per second. And, but actually this Lustre can do 10 gigabytes per second or more, but that's on a little bit lower tier with 100 giga, comprised of 2 nodes that I'll be showing it next. So how this works, so if the object storage, there's a myth that object storage is so slow, it's only for archival purpose or things like that. Things have changed with the AI. You do have a public object storage. They can be connected at 100 gigabits per second. And the real heroes hiding the latency are the ZFS as a ZFetch. It's pretty intelligent prefetch. And also Lustre from the client side, it can also do, it's got a lot of knobs for read aheads and things like that. So with this, you can achieve very good throughput with object storage, which is a low latency, with even on high latency, 30 milliseconds or 50 milliseconds storage tier. And for any IOPS related or small files, you have the special VDEV to cover that up. So again, for the write case, to cover the latency, yeah, that parameter, I think this is similar to the desync option of NFS, because you don't want to be syncing like for every IO. So you got to turn this 0. So that what ZFS does is it can do a heavy batching of all the writes, and every 3 seconds or 5 seconds, based on the transaction delay, it can flush it out. And so all these are relevant parameters. And for ZFS as a ZFetch, which is an intelligent prefetch mechanisms. And so it's not a simple read ahead. It can have it can have parallel streams open. You could open multiple files, and it can sense read ahead context for each file. And it can even detect out of order reads coming in. For example, yeah, if you do a direct IO from NFS and things like that, even though you are trying to do a sequential IO, the RPC can come in out of order, and it can confuse the ZFS thinking that it's a random IO, but it is not. So ZFS has some parameter wherein you can say how much amount of randomness I can tolerate. So there is a random IO size like 16 MB or things like that. So it can tolerate, keep the stream open. So what it does is when it senses the IO is random, it closes the stream. With the randomness parameter, it can keep it open. So, yeah, I just want to show you in a real workload here, which is the MLPerf ResNet 50. I think Microsoft engineer talked about that earlier in one of the sessions. And so I don't have to cover this again. And I think if you guys recollect, you mentioned that yeah, the H100 would need about 200 megabytes per second bandwidth for each H100 GPUs. And the type of workload here is, it is not real, it is kind of small file, like 150 MB files, but you'll have many 100K, several Ks of files. But what it's doing is it will read only like 200K. It's not going to run one full sequential run. unlike the other benchmark 3D UNet, which will read the full file in one shot, kind of. But whereas this ResNet 50 is kind of tricky benchmark, so what it does is it is sequential read only of all the 200 meg file, but it will read the file, it will sample it, and then it will shuffle to a different file. Like that, it shuffles around 200K or 300K files, depending on what your data set training is. So it's pretty challenging for the page cache, because they deliberately make the data set 5 times the client memory so that it doesn't fit in the page cache. So at the same time, it's shuffling around all these files, reading 200K. So you cannot have a full sequential run all the time. So the ZFS, ZFetch, and Lustre read aheads, all those help a little bit, but you have to use the page cache here because even if some residual data that was read, if it's lying around in the page cache, it can be helpful. So this is a pretty challenging benchmark, the ResNet 50, and if you guys notice that, like no NFS vendor, you see, if you look in the ML comments 2.2 submission results, you wouldn't find a NFS vendor, or they're not there. So you would see plenty of Lustres in there. Because the key point there is these benchmarks, they take a data directory option, and you can only specify one data mount point. And that kind of makes it difficult for NFS to get in there. And so for them to operate, they have to modify that benchmark to do their own striping and things like that. But then that is not considered as a closed benchmark so for submission. So that's a different story. But for us, even with the NFS, we could do like on object storage, we could do like half of it. For example, with these 2 nodes, you get 2 mount points, but you can only use 1 mount point, and you get like 44 H100. That's also a very good number to publish because the cost of supporting feeding a GPU, the 44 H100 GPU, is very little. You just need 2 instances compared to other real vendors. Like they have large clusters. It doesn't justify 1 mount point and 1 4400 GPUs being supported. So on the next slide, so what this thing does is it runs 5 epochs, and you could run like 3 times, and this 90% AU, that means that so this thing was only idle 10% of the time, so it's got to be above 90% for a pass mark. So again, this is the proof here that it was operating directly on the object storage. So no caching, nothing, right? No NVMe caching. So each epoch. So this is not a graph generated by us. It is image provided directly from the GCS cloud monitoring, where you could see the egress rate. So each of these constitute your runs. And so you could see like things like you got to be doing 8 gigabytes per second, and then you got to be supporting around that many H100s. So again, no NVMe cache. So everything directly coming from object storage. And again, the heroes are the ZFS prefetch and the Lustre read ahead doing the magic there. So it's reading like 50 terabytes in 3 hours, all from 2 VMs. So again, unconventional is about this architecture is, typically Lustre is in a fan-in. You have small clients, numerous small clients connected to servers. Whereas here it's the other way around. The client here is beefy. It's got like a 150 gigabits per second network. It's more cores connected to the Lustre server. So that's what makes it special for AI training. And again, NFS cannot reaches a dead end in this type of architecture. So I want to bring in in this slide, so compare NFS with the Lustre. How it is possible? Because the same MyNAS, it's basically, Lustre is sitting as one of the is a ZFS data set, and you can have another ZFS data set of the same pool, NFS or SMB. So that's why it's possible for us to compare. So you could see remarkable similarities from a client perspective. So you have the most common thing, the N-Connect 16. Without that, one single TCP connection cannot do anything, cannot deliver NFS throughput. And for Lustre, client equivalent, that's what I figured out is it's going to be the parameter on the KSOC canal. And for NFS, the sweet spot is 1 MB. And similarly, for Lustre, you could achieve that same 1 MB sweet spot by a combination of a couple of those parameters. Increasing any of those, there's no substantial gain out of that. And so direct, so Lustre has the same thing, like even to a hybrid plus the direct option too. So so on Lustre side, you could control the checksum. And for the read, the NFS and Lustre seem to be the same. For NFS, you got to use the 2 mount points, obviously, to match with the Lustre if you're running with the FIO. But in the right scenario, the Lustre is pretty smooth compared to NFS because that's where the protocol superiority is there. And the way the Lustre is architected, it can directly write to the ZFS DMU engine. So the data goes and lands in the ARC DMU. So Lustre can do writes about 7 gigabits per second in this particular configuration, whereas NFS can do only about a little bit shy of that. Because the way the sync works over there is it's like they try too many things for F-sync, whereas Lustre seem to handle it pretty nicely. Because with the NFS, you have combination of commit protocols being issued, n number on a close also it could be issued. So that's like many things that they could be trying on F-sync. There's unpredictability. With the Lustre, the right path is smooth. And for a read buffer, Lustre and both pretty much the same. And for buffered also it matches. Okay. That maybe running out of time here. So it's again active 2 nodes. So I'm going to talk about the challenges here, and some of them I think probably there was an overlap with the OCA, Oracle folks too. They probably mentioned the same thing, I guess. This seems to be a common thing whenever somebody deploys with a VIP or a virtual IP or a floating IP. So if the first thing is you got to file fast enough so that the clients forget about the failed node, and because the surviving node can come up so fast with the VIP. So that's one issue, and the second one is the LNet loopback. Because this is also because of this architecture, you try to combine the MDT and one of the OST, MGS, everything in one node. They try to figure at one point during bring up, they would be remembering the loopback instead of the VIP. So things like that. So we have to forcefully detach and make it operational. And then third thing is the multi-rail auto discovery that, the Oracle folks also mentioned that. So you have option to disable that peer discovery. So in terms of failover, the Lustre is clean, so not much time taken for a failover. I think that the failover could be variable for the Z pool. Object storage, depending on the, so luckily the metadata is sitting on the NVMe with the special and object storage hybrid architecture. But there is an option, you don't have to walk the object storage for recovery, but still it's good to walk, I mean, for safe of mind, it's better to walk the object storage. So just a comparison of cloud native with the traditional Lustre. Cloud native when you use object storage. So here it is. Like, so if you guys want to try it out, this is how. So it's totally free. So the infrastructure for the cloud, obviously, there's a cost for that. But for the software, Lustre, everything is free. So you clone it, and once you have a configured Terraform, you deploy it, and within 2 minutes, your Lustre should be available, and then you can do LFS check servers on the client, and you should see all the components. So say we come to the end. So for the questions.
Yes, I have one question. You were comparing Lustre, but did you try the same test with GCS Fuse, directly talking to actually GCS?
With what, I'm sorry?
So for the benchmark, for DLL benchmark, the test was like Lustre going to GCS. Did you try directly connecting to GCS, maybe using GCS Fuse or any of that?
Or you want me to compare with the GCS Fuse? I'm not familiar with GCS Fuse.
Okay, I understand.
Yeah, I know. I think they have a combination of expensive rapid storage buckets and things like that. But this is a simple standard object storage, 2 cents per gigabyte. Yeah. So, but the numbers are out here, and the performance numbers I've given. So, if they have the numbers, then we could just compare.
Back on your architecture slide, you were using TCP. Why were you using TCP instead of RDMA?
RDMA instead of RDMA?
Yeah.
Because it's not available on public cloud. Only AWS has EFA, that's proprietary. And OCI has RDMA. But then we are on 3 clouds only. So there is no RDMA, that's the short answer. But we could do RDMA if it's available.
On AWS at least, the EFA driver is in tree, so you could use that even outside of like FSX for Lustre if you wanted.
Yes, yeah, exactly. Yeah, EFA is there. And that's available only on high-end instances, right? And here with the GCP, you get 50 gigabits per second, even on a 32 core. In a tier 1, that's all the specialty, right? We do tier 1 configuration on the instances, everything taken care of by Terraform module.
Apologies if I missed this. Did you say on the ZFS layer, there's like, you don't use NVMe or anything local to the actual like OSSs to try and avoid churning in the buckets? Like, I mean, you can pay IO costs if you're going to and from those buckets like all the time. So are you just going there for like every IO? Like, are you caching some of that stuff?
No, the heroes are the Z-fetch for the read. In the read scenario, the caching, the Z-fetch, it builds a bigger pipeline for the read scenario.
Right.
If you for a throughput like a ResNet workload, it can build the Lustre read ahead on the client side, builds a pipeline to hide the latency of 30 milliseconds. And similarly on the ZFS backend, it can also hide the pipeline. The Z-fetch layer takes care of that by reading it and keeping it into the ARC memory cache.
Sure.
Whether it's going to use it or not, it will fetch. If it sees the sequential run, it will fetch and keep it in the ZFS ARC. And it will throw it out if it doesn't see the sequential hit. So that's on the read side. For the write scenario, yeah, so it's all like batched. The writes are landing up, the concurrent writes are coming in. They land in the ARC cache. The TX, that's a transact TXG daemon, syncing daemon, which accumulates like every 3 seconds or 5 seconds, tunable parameter, and then it batches them and it writes concurrently. So when it writes, there are so many knobs in ZFS, like the VDEV layer, you can do like 1,024 requests out to the network, and you could see like over 1,000 HTTPS connections to the bucket, storage buckets. So all are written directly at the time. So there is no caching.
Okay. Yeah. No, my point was more that like we've also talked about like blob, almost like a direct to blob like OST, but we've always been like the cost will be too high over time if you are constantly for every IO on a specific file. If you're not doing some level of caching to eliminate, I mean, files that are created and then deleted like quickly thereafter, things like that. It would just, the IOs going to and from an object storage for any of the hyperscalers incur costs.
Yeah, so there can be like, yeah, there is to some level it is covered. On the client side, the page cache covers it, and then the back end, the ZFS covers a little bit. And beyond that, if you have to hit the storage anyways, it's not only that there's a performance cost and also the API cost. Like, and the API cost, that is why we use the block size as 1 MB. That's the purpose of that.
Got it.
So you try to reduce the API cost. So in 1 MB, try to fetch as many blocks. Yeah.
Thank you.
You could configure it to 4 MB also if you want.
Any more questions for our speaker? Let's give our speaker another round of applause.